Problem number 17, consider the probability that fewer than 13 out of 155 houses will lose power once a year. Assume the probability that a given house will lose power once a year is 10%. Approximate the probability using the normal distribution. All right, so first of all, the problem said less than. So it said the probability that less than 13. So that's very important to what we're doing. So whenever we start doing our calculations, the x is going to equal 13. This is with proportions, and this is with the continuity correction, right? So, because it says approximate the probability using the normal distribution, round your answer to 4 decimal places. So we're going to have to do the same. Well, in the last problem, we only had to tell where the area would be. Now we're actually going to calculate it, okay? So with continuity correction, let's see, fewer than 13. Well, we need a couple of other values that aren't just given to us. It says, assume the probability that a given house will lose power once a year is 10%. So we have to take 10% of the total number of houses. That gives us our mean. Our mean is n times p. Our mean is n times p. And so the number of houses was 155, and it said there was a 10% chance, so that's 0.1. So the mu that we're going to use is 15.5. The x we're going to use is not going to be 13. Oh, I wrote that down. Because remember, continuity correction, we have to first write down what we're looking for, less than 13. And then we have to come to this chart, and if it's less than, it says we need to say minus 0.5. It's the same thing we did in the last problem, even though the last problem was greater than or equal to. For less than, you have to do minus 0.5 as well. Okay, so our x value is going to be 13 minus 0.5. So we got to subtract 0.5 from that, which would make our x 12.5. All right. What else do we need? Well, for our z-score, we need a x, we need a mu, we need a sigma. So we need the standard deviation. Okay. The standard deviation is going to be equal to the square root of n times p times 1 minus p. That's how we find the standard deviation for a binomial. All right. So for what we have, that's going to be the square root of 155 times, we were given that probability of 0.1, and then we had to say that times 1 minus 0.1. 1 minus 0.1 is 0.9. All right, so we multiply those three numbers together, and then we take the square root, and when you do, you get 3.734969. Now, since we're going to have to use the standard deviation in a formula, I would carry it out to many places like that. So we have z equals x minus mu over sigma, or 12.5 minus 15.5 over 3.73469. All right. When you do that in your calculator, then remember the answer that we get, we want to round to 2 places because it's a z-score. So when you do that in your calculator and round, you'll get negative 0.80. So this is the z-score that we're going to use to figure out the probability. All right. Now remember, this is just an approximation. This isn't exact. So you may be wondering, why do we even do these approximations for binomial? Or by using the binomial, why do we want to approximate using the standard normal curve? It's because if you remember the binomial probability problems, remember that binomial formula? If I wanted to know less than 13, I would have to do a formula for 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and 0. And imagine if it was greater than 13. Well, that could just go on forever. So before calculators were invented, we had to figure out ways to approximate these things because it wasn't feasible without using calculus to be able to do this. So that's why we use this standard normal curve to approximate this binomial situation. All right, anyway, let's get back to the problem. This was a less than problem, so that means I'm going to actually take the area that's given to me. Remember, less than is area to the left. Well, that's the way that my tables work. So I just need to bring up my table. I don't see it listed here, so you can push the table button, go to standard normal table. Remember, our z was negative, so we need this one, negative infinity to negative z. And we want to look up a z-score of negative 0.80. So the hundredths, the 0 is we're going to have to scroll. Can't even get to it. I'm going to have to, there we go. So I have to scroll over negative 0.80. So that's our answer. That's our probability we're looking for. Hopefully by clicking on it, it put it in the blank. If it didn't, I'll put it in there. 0.2119. It didn't. That's okay. All right. All right, number 18. Select a scenario in which is an example of voluntary sampling. All right, so voluntary would mean, of course, you have to volunteer. And if you read through all of these, it looks like this first one they're picking out numbers, so you wouldn't have a choice if you were chosen or not. Now, would you have a choice to do it or not? Yes, but here there's really no choice because the city managers are selecting them. If you read through each one of these, the only one that's voluntary would be the last one. It says a magazine wants to write a story about its readership's eating habits and ask readers to send in their responses to the question, how often do you eat fast food? So like, not everybody's not going to respond to that, but people who are interested in this magazine, they would write in and say, may or may not. It's voluntary. So the answer is this last one here. Okay. Which of the following is a good point estimator for the population standard deviation? So for standard deviation, mean, median, those types of calculations, the best point estimator we have is the one we would get from the sample. So for a population standard deviation, it would be that the symbol for population standard deviation is this one. This isn't the answer. All right. The estimator is the one from the sample. So the variable we use is S, right, for standard deviation. It's the square root of the variance. So this is the best point estimator for the population standard deviation. All right. Suppose a batch of metal shafts produced in a manufacturing company have a standard deviation of 2.4 and a mean diameter of 209 inches. If 69 shafts are sampled at random from the batch, what is the probability that the mean diameter of the shafts would differ from the population mean by less than 0.1 inches? Now, this one is a little different than we're used to. There's two things that are different. All right, first off, since we have 69 shafts sampled, this is a central limit theorem problem. All right, and the thing about central limit theorem problems is that instead of just having a sigma, we have a sigma sub x bar, because it comes from a mean of a population, or at least we're trying to figure out a probability about the mean of a sample group. And so we have to use our sigma sub x bar, which is sigma divided by the square root of n. So when we do our z-score, it's x minus mu over that sigma sub x bar, which is sigma over the square root of n. So that's one reason why this is a different problem. Another reason is it doesn't actually give us the value. It gives us a value for a margin of error, if that makes sense. It wants to know what is the probability that the mean diameter of the sample shafts would differ from the population mean by less than 0.1 inches. All right, the population mean is up here, 209. Now you try to plug this in as your x value, 0.1, and you're going to get a z-score so big that it's not even on the tables. You know, the biggest z-score on the tables is 3.49. The smallest z-score on the tables is negative 3.49. If you're looking for something other than that, you probably messed up, because you usually don't deal with any values bigger or smaller than those. So how do we figure out would differ by less than 0.1 inches? Well, that would be 0.1 inches bigger or 0.1 inches smaller. Be both of those. Okay, so we're going to have two x values here. So I'm going to write down what I have. I'm going to write down the standard deviation, the population mean, the sample size n, and then we're going to have one x value larger than the mean and one x value smaller than the mean, both by 0.1 inches. All right. So we had the standard deviation of 2.4 was given. That's population standard deviation. We had a population mean given of 209, and we had a sample size of 69. Again, we're going to have two x values, so we're going to have to solve two problems. And then since it said is less than 0.1 of the population mean, we want the area between the two. So if I subtract 0.1 from the population mean, that'll be 208.9. If I add 1 to the population mean, that'll be 209.1. Now we're going to have to find a z-score for both, and then we're going to find the area between the two, and that will give us the probability that the mean of a group of 69 of these items would differ by less than 0.1 inches. It's a little confusing, but I'll show you under the curve before I start doing my calculations. You know, if you have z equals 0 right here in the middle, it really depends on what z values we get. I already know the ones that we're going to get. So we're going to have one that's going to be really close here on the right, and we're going to have one that's really close here on the left. And I want to know the probability that the mean of 69 of these would be within 0.1 inches of the mean of the population. So that's everything in between. Okay? If it wanted to know greater than 1.1 inches, it would be everything on the outside of both of those. But since it wants to know less than 0.1, that's between the two. All right. So I need a z-score for both of these, and the z-scores are going to be very similar. I'll go ahead and give you a hint there. If you've done the homework, you know what I'm talking about. So z equals, let's start with the first x I wrote down, 208.9 minus the population mean was 209 over, and now we have to use this special thing because we had a sample of 69 of these. So the population standard deviation was 2.4 divided by the square root of the sample size. Now, if you do this in your calculator, there's a lot of ways to do this. Just if you're going to do the numerator and denominator separately, don't round the denominator. Or if you do round it, take it out to about 5 or 6 places. Because if you don't, remember we have to round the z-score to 2 places. And if you round this denominator to just a couple places, and then you divide, you're creating a big margin of error there. I'll show you one way you can do it in the calculator. For some students this may confuse you, but for some it may make a little more sense. If you work out the numerator first, so 208.9 minus 209. Alright, then we take this denominator. If you flip the denominator and multiply it times the top, what you'd really be doing is multiplying what you get in the denominator by this square root of 69. So I could say times, and in this calculator I have to do 69 square root equals, and then I would have to divide by 2.4. Divided by 2.4. Alright, and so that's what you should get in your calculator regardless of how you punch it in. You should get something close to that. If I round that to 2 places, you can see it's going to be negative 0.35. Alright, and so now let's find a z-score for the other. It's 209.1 minus 209 divided by the same numbers as before. Now look what happens here. Take a good look at that answer. Whenever I say 209.1 minus 209, I get the same numerator as before, except it has the opposite sign. So if I'm dividing it by the same thing, so I would, if I do the same thing, flip and multiply, that will be times the square root of 69 equals divided by 2.4 equals. You see I get the same answer except it's a different sign. On problems like this where we're looking around, we're adding and subtracting the same number from the population mean, that's always going to happen. You're always going to get the same number. It's just one of them's going to be positive and one of them's going to be negative. So if that helps speed up your work, use that. If not, you can calculate them both. It doesn't matter. Alright. So right here where I drew this picture, that's around a z-score of negative 0.35. And then right here, that's around a z-score of 0.35. Because remember, positive z-scores to the right of the center, negative z-scores to the left of the center. If I want to find the area between the two, there's a couple of ways to do it. If you want to stay consistent in what we've been doing all along to find area, find the area of the one on the right, and then find the area of the one on the left, and say the bigger area minus the smaller area. So to do those, you look in the table, in the z-score table. So look up a z-score of 0.35. When you do that, you should get, you're going to get 0.6368. Then look up a z-score of negative 3.35, and you're going to get 0.3632, and subtract. That will give you the area between the two. Alright, so I got the area between the two is 0.2736. So I probably didn't go out far enough whenever I drew this, but because that should be about 27% of the area under the curve. Alright, that's your answer. That's my answer. So 0.2736. Alright, so this is a similar problem. The only thing is, it doesn't ask us to add and subtract about the population mean. Okay? So if you read through this problem, it says there's a population mean of 331 with a variance of 144. We don't need the variance in our formulas. We need the standard deviation. So we're going to take the square root of that. Okay? And then it says, what is the probability that the mean amplifier output would be greater than 332.8 watts in a sample of 49 amplifiers if the claim is true? Alright, so this is a greater than problem, but this is our actual x value. We don't have to add and subtract anything from the population mean. Alright. So I'm going to work a little quicker through this one because this is very similar to other ones that we can work. The only thing that's different is the central limit theorem makes us do our standard deviation a little differently. Okay? So in this problem, we were given a mean of 331. That's the population mean. The sample size was 49. We were given the variance, which was 144, but we don't need the variance. We need the standard deviation. So the square root of 144 is 12. And then our problem was, what's the probability that the output would be greater than 332.8? So our x value that we're going to use, and it was the probability that the mean of these 49 items will be greater than that. But our x value we're going to use is 332.8. So let's find a z-score. So x is 332.8. The x always comes from the sample. Minus the population mean is 331 over, it's not just sigma, remember, because we have a sample of 49 things. So it's going to be 12 divided by the square root of 49. The square root of 49 is 7, so if you want to write that there, that's fine. Do that work and round, and you should get 1.05. Alright, this is a greater than problem. So what that means is, I want to know the area to the right. So if this is the center, and I'm one standard deviation to the right, if that's z equals 1.05, I want to know the area to the right, because that will give me the probability for a greater than. To do that, I look up this z-score, and I'll say 1 minus the value when I look up the z-score. Okay. So to go to the tables, click Table. Remember, it was 1.05. So standard normal table, negative infinity to z, 1.05. So this is what I'm subtracting. All right, 0.8531. 0.8531. So I say 1 minus 0.8531. Why is it 1 minus again? Because this was a greater than problem. All right. When you do that, you get 0.1469. Don't just put 0.8531 in as your answer. A greater than problem, we have to say 1 minus. 0.1469. This looks almost exactly like the last problem. You don't have to add and subtract anything from the given mean. It does give you the standard deviation. That's good. The sample is 100 people, but the only difference, I guess, main difference is this is a less than problem. What is the probability the sample mean would be less than 122.27 liters? Okay. So let's write down everything that we have. The population mean was given to be 126. The population standard deviation was given to be 24. It told us that our sample size was 100, and we want to know the probability that the sample mean will be less than 122.27. Less than problems I like because I know that I'm just going to be able to look up the value in the table if it's a single value like this. Alright, this is a central limit theorem problem because we have a sample size. So our z-score is, this is our x, the number that comes from the sample, x minus mu divided by, and then remember it's not just sigma, it's sigma, the standard deviation, over the square root of n. And yes, the square root of 100 is 10. You could just write a 10 there if you want. After you do this calculation, hopefully in your calculator, and round, you'll get negative 1.55. Alright, so since this is a less than problem, we look this up in the z-score chart. The answer it gives us, the area it gives us, is the answer to the problem, 0.0606. So I didn't look it up because I'd already looked it up earlier, just to save time. Alright, these last three problems are similar to what we've been doing with the central limit theorem. The only difference is you'll see instead of means we have percentages. So those are proportions. So all three of these problems we have to use different formulas, but we're doing the same thing. It's just we're using proportions instead. So the three formulas that we're going to use, or I say three formulas. For our z, what do we need? We need an x, we need a mu, and we need a sigma divided by the square root of n. Well, the way that we calculate these, if they're not given in the problem, are a little different because we don't have a mean anymore, right? We have a proportion. So that's going to change a little bit, okay? So instead of an x and a mu, we're going to have a p and a p hat, where p is the population proportion, p hat is the sample proportion. Okay? And I may have written that backwards. So we always say sample value minus population value. Sorry about that. We always want to put the value from the sample first. Now to calculate this right here, instead of this being it's no longer a mu sub x bar. Okay, it's no longer that. It's a mu sub p value. Okay, so to do that, we have a special formula that we use. It's the square root of p times 1 minus p divided by n. So these are the population values. Okay, and that's what goes down here. The square root of n is there, so all of this will be now replaced with this. Okay, so on this problem, let's look at the values we were given really quick. It says suppose 40% of students in the university are baseball players. So that's our p, 0.4. We have a sample of 781, and we want to know what is the probability that the sample proportion of baseball players will be greater than 43%. So this comes from our sample, so that's our p hat. Okay, so we have a p, that's the population proportion. That was 0.4. We have to write that percentage as a decimal. We have a p hat, and we want to know the probability that p hat is greater than 43%, so that's greater than 0.43. And we were given a sample size. The sample size was 781. Now what we were not given was what we need for the denominator. This right here, this n is going to have to, we use that in our formula to get what we need in our denominator of our z-score. So that's going to be the square root of, and again, these are population values. So we don't use the p hat here, we use the p. So it's 0.4 times 1 minus 0.4 is 0.6 divided by 781. Now, don't forget that once you do all of these calculations in here, you have to take the square root. And you want to take this out to several places. Because again, we're going to plug this in a formula, and we don't want to plug values in a formula that are rounded too close to the place where we're going to have to round in the formula. In the z-score formula, we have to round to 2 places. So at least carry this out to about 5 to be safe. Okay? So now we want to find our z-score. It's always going to be the sample value, which was p hat, so that's 0.43, minus the population value, which was 0.4, divided by this long decimal here. Now, when you do that, type all that in your calculator and round your z-score. Your z-score is going to round to 1.71. Now, since this is a greater than problem, when we look this up in our z-score chart, we're going to say 1 minus what it gives us, and that will give us our answer. So we go to our z-score chart, and we look up 1.71. So there's 1.71. We're going to have to say 1 minus that, and that will be our answer. So 0.9564. 0.9564. That's not our answer. That's what we have to say. We have to subtract from 1. Type that in your calculator, and you get 0.0436. That is your answer. That is our answer. All right, now look at the next problem. It's not going to change much. 40% still, 781 still. The only thing that changes in the problem is I made it less than 43%. So all of the calculations that we did, that we've already done, we can use those calculations. All right, the only thing is, on this problem, the only thing that changes is that we want the probability that p hat is less than 0.43. Okay? So I just wanted you to see the difference between a less than and a greater than using the same values. So here we had p was 0.4, we had sample size was 781, and we remember we had already calculated our sigma sub p. It was 0.01752997. There's no use in us writing everything down. The main thing that we have is we know that z is going to be 1.71. Since it's a less than problem, we just want to take the value from the table. Well, we did that earlier. Remember, earlier we had to say 1 minus that. It was 0.9564. So that's what we're going to put in. 0.9564. And the last problem. All right, so this is just like those problems, the few problems we've worked before this. In the problem, we are given the population proportion is 17%. We want to know the probability that p hat is less than 0.13. We have a sample size of 683. So to find our sigma sub p, that's going to be the square root of p, which is 0.17, times 1 minus p, or 1 minus 0.17 is 0.83, divided by n, 683. Again, when you multiply and then divide, remember you have to take the square root at the end. When I did that, I got 0.0146. 37319. And I carry it out that many places because I have to plug it in a formula. So remember, your sample value always comes first. So that's 0.13 minus 0.17 divided by this long decimal we just got. When you do that, you get negative 2.78. This is a less than problem. So that means we want to look at our table and we would just want to take the area we're given for negative 2.78. Let's do that. So I'm going to pull up my tables. Standard normal table. I need the negative one. Negative 2.78. This is our answer. I'm going to just copy it. Okay? If I copy it over, I'm pretty sure I can just paste it in. And that's your test review. Alright. So if you have any questions, let me know. And you can work through this as many times as you want. If you have any questions about it, just let me know. And hopefully you will make a 100% on yours as well. Thanks. Have a great day.